Hello and welcome to section 1.1 in Pre-Calculus Trig. This is part 2 of our lecture on angles and their measure. So let's do a brief vocabulary review on some angle terminology. An acute angle is an angle that's less than 90 degrees. A right angle is an angle that's exactly 90 degrees. An obtuse angle is greater than 90 degrees. A straight angle is equal to 180 degrees. Supplementary angles add to 180 degrees. Adjacent angles share a side. Complementary angles add to 90 degrees. So next, let's talk about arc length. So when we talk about arc length, we mean what is the length of this distance here, a piece of the outer rim of the circle, basically. So it's called the length of a circular arc. So that's a piece of a circle. And here's this word subtended. Subtended by the central angle theta in radians. So that simply means if you have an angle theta as drawn in this picture here. So this angle theta, here's your center, is between these two radii. This here is considered the arc subtended by this angle theta. So S is your standard variable that we use to refer to arc length. So the units of the arc length are going to be the units of the radius. So if this radius was in inches, then this distance here would also be given in inches. That's generally how you're going to see this. So we have this formula that says the arc length S is equal to R times the angle theta, where theta here is in radians, not degrees. So if you're given your angle in degrees, you're going to have to convert it into radians by multiplying it by pi over 180. So we're going to do some problems like this now. So this problem says find the length of the arc of a circle of radius 7 feet subtended by a central angle of 120 degrees. So let's draw a picture. So here's our picture. So we've got a circle with a radius of 7 feet, and we've got a central angle. Here's our center of 120 degrees. So if I take this as 0, I'm going to go 30 degrees past 90. So this is a rough sketch. This angle right here is 120 degrees. So I'm looking for the length of my arc here. That would be my S, subtended by a central angle 120 degrees. So that's my S. Now our formula is arc length is equal to R times your angle, which subtends that arc. And we need to be working in radians. All right, so we're going to say S is equal to 7 feet times our angle in degrees, which is 120 degrees, which I'm going to convert to radians by multiplying by our conversion factor. So that way, my degrees will cancel, and I'll be left with feet. All right, radians are unitless, and that's how they work out really well with a problem like this. So we would just simply call our units feet. So I've got 7 times 120 times pi divided by 180, which I would want to plug into my calculator. So I got a number here of 14.66 feet. Now let's see if that makes reasonable sense in my diagram. So that's roughly 2 radii. So we've got 7 feet, so that would be 7 and 7. So that's reasonably in the ballpark. So that's our answer here. So let's highlight that. So you always want to check and see whether the magnitude of the number you come up with makes sense, so you can catch any mistakes you might have made along the way. So this example says find the length of the arc of a circle of radius 22 miles subtended by a central angle of 4.2 radians. Find the measure in degrees of the angle that subtends an arc of length 10 miles. So this is two problems. All right, so let's do the first one. Find the length of the arc of a circle of radius 22 miles subtended by a central angle of 4.2 radians. So I'm going to make a sketch. I recommend you make a sketch first. So here's my circle. So here's my radius of 22 miles, and I have an arc of 4.2 radians. Well, exactly what does that mean? So let's see, I'm at 0 radians here. I'm at pi radians over here, so pi is 3.14, and then I'm at 2 radians, 2 pi radians, over here, so that's 6.28. So I've got 3.14, let's see, if I add another, this is pi over 2 radians here, half of 3.14, so if I add another 1.57 onto here, that'll give me this number here. So that's 4.71 radians. All right, so 4.2 radians is going to be roughly about here, which gives me an angle right here, 4.2 radians. So that means I'm looking for the arc. Let's highlight the arc subtended by that 4.2 radian angle. All right, so we're looking for this dimension here. So let's write our formula. S is equal to r times theta, where theta is in radians. So we're already in radians, so we're just going to multiply r times, which is 22 miles, times our angle in radians, and we'll just get that 22 times 4.2 is our distance of that green arc. All right, so it's pretty straightforward to see that that makes sense, because approximately 4 times 22 is right in the ballpark of this number right here. So it's just the number of radians times the radius without a conversion factor required. So this is your answer here. Second part of this problem says find the measure in degrees of the angle that subtends an arc of length 10 miles. So 10 miles is roughly half of the length of the radius, which is 22 miles. So if I imagine that 22 miles as a piece of string on the outside of the circle here, halfway would be about right there. So I'm just going to draw a rough sketch. So this is my angle theta here. So let me put my 10 miles on here. This distance is said to be 10 miles. All right, now our formula, arc length is equal to r times theta. Now this time we want to know what the angle is, because we don't know that. We do know the s, so we're going to say let's divide it both sides by r. So we'll have the angle is equal to s divided by r. All right, so let's plug those numbers in here. So I've got 10 miles divided by 22 miles. So that equals 5 over 11. All right, so notice that I don't have any units, so that's in radians there. My angle is in radians. But I'm asked for degrees. So now I got to convert that number. Let's go down here. So if I'm in radians and I want to convert to degrees, I want my degrees on top, my radians on the bottom. All right, so I'm going to punch that into the calculator. So that's just 5 times 180 divided by 11 pi. So I punched that in and I got roughly 22 degrees, so that is a small angle, so that makes reasonable sense. So we're going to highlight that. Next, let's talk about sector area. So a sector of a circle is formed by a central angle, which just means that your vertex of your angle is in the center of your circle. So this orange piece right here would be a sector of a circle. So the area of a sector is a proportion of the total area of the circle. So the total area of a circle we know is pi r squared. So the way that we would proportion that would be my area of my sector is equal to the total area of the circle times my theta here divided by the total degrees in the circle, and that'll give me my proportion. So in this formula right here, theta is in degrees. If you were given your theta here in radians, then your proportion would look like this, where in this case 2 pi is your total revolution around the circle, and theta would have to be given in radians. So either one of these two formulas right here, depending on your given information, would be used to find sector area. So in this example, we're saying find the area of a sector of a circle with the radius 8 inches formed by a central angle of 165 degrees, and here's a second problem, and by a central angle of 6 pi over 7 radians. So we'll do it both ways. So let's draw a quick sketch. Okay, so I made this little sketch. So my circle of radius 8, and we're asked for the area of this sector here in pink, which is formed by a central angle of 165 degrees. So that's less than 180 degrees, so about here. All right, so we're going to do this part first. So we're going to proportion the area of the entire circle, which is pi r squared, by the proportion of the circle that is pink. So that's 165 degrees out of 360 degrees total. All right, so I'm proportioning my area. So let's put the r in here. So that's 8 times 165 over 360. All right, so I'm going to plug all that into my calculator. So you would say pi times 8 squared times 165 divided by 360. So I got the number here, 92.15, and my units of area are squared inches because I started out with inches. My area units are always squared. So this is 92.15 inches squared is the area of this pink sector. All right, so let's try the second part of our problem here. So let's estimate on our diagram how much 6 pi over 7 would take up in the way of a sector. So 7/7 is equal to 1 pi. All right, so that would be this far. So it's not quite half of a circle. So let's put it about here. All right, and that would be my central angle, 6 pi over 7, and that would be in radians. So we know the area of the entire circle is pi r squared. So this is our total circle, remember? And we want to proportion that by the amount that we have relative to the entire full circle. If we're working in radians, a full circle is 2 pi radians, 1 full revolution, but we've got 6 pi over 7 radians in this problem. So let's write that a little better. So there's multiple ways we could write this other than how it's written now. Let's do this. We've got pi r squared times 6 pi over 7, and then we're divided by 2 pi, so we can write it like this. That's one way to do it. So we can cancel some pi's out here, like this. All right, so I've got pi r squared, where r is 8. So that's pi times 8 squared times 6 over 7 times 2. Let's just say that's 14. All right, so you can go ahead and plug that into the calculator. So I get 86.17 inches squared. So that's the area of the pink portion of my circle. So we've answered the question, either in degrees or radians, how to find the area of a sector of a circle of radius r. All right, so that wraps up our examples for section 1.1 in Trig of our pre-calculus course. Go ahead and attempt your homework problems now in 1.1 and let me know if you have any questions.